Okay.
Okay. Well, good afternoon, everyone. Thank you for joining us this afternoon. Let me introduce our speaker. It's our collaborator here, Professor Philippe Leclere from University de Mons. French, right?
Correct.
Correct. The University de Mons from Belgium. He is visiting us here during this week, visiting our laboratories. He met some of our professors and students. And thank you very much for coming. I know it's a very far place to come, and not so easy. So I thank you very much for joining us this week. It was very nice. Well, I was reading here his summary of his life. It's very long.
Make it short.
So a lot of pride and awards and professional positions. But since 2021, he is the head director of the laboratory for the physics of nanomaterials and energy, LPNE, right? The place I visited last May. So he has a lot of he's a membership of a lot of organizations like Royal Belgian Society of Microscopy. He's the president, right? The president of the Royal Belgian Society for Microscopy. President of the Prom Optica, president of NanoWall, and a very long list of memberships, positions, awards, and well, I invite you to see his CV or visit his website. I will basically tell he works with the state of the art of scanning probe microscopy. So he will present here his lab, his facilities, and everything else. The title you can see here: Nanoscale electrical characterization of organic and hybrid materials for energy applications. Energy is what matters, right? The logo, yeah, it's perfect. So thank you very much for coming. Enjoy the seminar.
Okay, obrigado, Alex. Obrigado.
De nada.
This is the only word I can pronounce in bon dia. Okay, thank you, Alex, for this nice introduction. So, as he mentioned, I'm here because we have a collaboration. I will show you in a minute what we are doing, and I will present the facilities. So, just the first part is also the goal of my visit is to try to get some collaboration together with the Mons and UFPR here in Brazil. So that's the opportunity. So feel free to ask questions at the end of the presentation. So as I said, so this is the code that we answered a few years ago with the confab and Wallonie Brussels. So this is the between confab and the Wallonie Brussels code, and we applied and we got the money to visit, which means that I'm here. But Alex came last May, and some of the students came also join University of Mons to make some experiment and to discuss with us. So as the outline of my talk, first I will put the context of energy. You know that it's extremely important to consider energy nowadays. Then I will shortly present some research team that we have at the LPNE, Laboratory for Physics of Nanomaterials and Energy. And then I will more focus on the SPM equipment. We have 3 levels of equipment. I will just focus on the scanning probe microscopy facilities and what we will get in the next coming month in our lab. And then I will show you some examples just to illustrate what we can do with this equipment concerning energy application, being batteries, organic solar cells, and light-emitting diodes. And then some conclusion and questions. So if you consider the evolution of energy from the pre-animal domestication, most of the energy are coming from biomass. People are just take some piece of wood, put the fire, and they got the energy out of that. And after that, what they got, they start to use some animals by using cow or horses. They use this energy to help them for agriculture, for instance. And then came in the mid of the 18th, we discovered coal for good and bad reason, of course. Then we have the oil, and you see that nowadays, at least in the 80s, oil was the most important resource of energy, and then came the nuclear power. So you see with the evolution of time, we try to find new source of energy to help us to have better life, to make the work that people don't want to do, and just the vapor motor, for instance, and all the engines are using those coal or oil or nuclear power. So if you look at the world energy demand, for the moment we need 25 or 26 terawatt hour. We don't know what it is, 25 terawatt hours, but if you look to the evolution, you see that this is on this scheme, you see the evolution of the energy, and you see that in 2040, which is tomorrow, what we will have is 80% of the energy will come from the sun. For the moment, 2/3 of the energy that we are using are coming from fossil fuels, but you know there's the sources are finite. It means that one day, tomorrow, in 2 decades, we have to find solutions. And in 2040, 80% of this electricity, of the global electricity, will be or must be generated by renewable energy. And as I mentioned, solar photovoltaics is certainly one good resource of energy. And if you look at the price, even if it's written in yen, we don't care. The idea is the power, the cost of the power. You see that nuclear power is quite inexpensive and can produce a lot of energy out of nuclear power. And you see that the photovoltaics is going down, and we hope that in 10 years we have the same price to produce 1 kilowatt hour from solar cells compared to nuclear. On the other hand, you see that the oil will be extremely rare and more expensive, which means that we have to find those solutions. If you look now, the source of energy, as I mentioned before, you have the coal, you have the gas, you see they are finite, okay? Which means that in a few decades there is no more gas or petroleum or even uranium for nuclear power. But here you have the sun, and actually, when the sun is shining outside, but there's already a sun somewhere on the Earth, you have 1,000 times energy you need for 1 year, which means that the sun can be considered as an infinite resource of energy. And if you remember your lecture about astronomy and so on, with evolution of the sun will grow. We will completely burn before the end of the sun. So, which means that unless people will destroy the planet, we will are safe and consider the sun as an energy, infinite solar energy. So we can also try to get, and this is a part of the activities of the lab, is try to get to harvest the energy coming from gravity, versus energy, from heat, from vibration, and so on. And the idea by using different techniques, like your piezoelectricity, thermoelectricity, try to produce electricity out of this energy. So if you look what we know for the moment, we know of course about alkaline batteries, lithium batteries. We know now it's commodity product for the moment. And you have those techniques of energy harvesting, it's more emerging technologies. And among the activities of the lab, we are working on photovoltaics, including perovskite photovoltaics, but also inorganic organic solar cells, I will show you some example later in my presentation. And we are also working on thermoelectricity and on the piezoelectricity. So these are the new, you are coupling the mechanical properties or the thermal properties with electricity. Of course, you are generating as a nuclear power can do, but you can get some energy for watch or for different sensor, human body, for instance. And for the battery and the supercapacitor, it's already on the commodity market. So that's why, as Alex mentioned, 2 years ago, I left the National Science Foundation to found and to a new lab, which is a laboratory for physics of nanoparticles and energy. And our motto is energy, nothing else matters. If you remember Metallica, comes from that. So more seriously, so the research, if you are working in material science, and we are involved in the Institute of Material Science at the University of Mons, if you want to make the link between the structure, the properties, the performances, and the process, if you are an engineer, what is in the center of this tetragon is the characterization. So what we are developing in the lab is characterization techniques, trying to understand how the molecule or the matter is organized to make a better and recyclable solar cells or to improve the process. So what we are doing actually, we are studying the morphological, mechanical, electronic, optical, and transport properties of organic materials. And among these materials, we have polymer blends, block of polymers, nanocomposites, hydrogels, and a lot of materials for organic electronics. We try to understand the self-assembly of these macromolecules and try to determine the structure and the electronic properties. You know, in solar cell, we have to tune different HOMO, LUMO, and these things. So the idea is really what people are calculating, or the chemists are synthesizing some molecule and we are checking that indeed they can provide the expected properties. Then we have the scanning probe microscopy, and we'll focus more today on this. And quite recently, 2 years ago, we are developing machine learning algorithms because we are generating a huge amount of data, which is humanly impossible to treat. So we ask the computer to make the data clustering or to use some model and so on just to treat the data. I will not discuss this point today with you, but we can discuss later, of course, this point. So what we are working, as I mentioned, morphology, mechanical, electrical properties, combined properties, for organic electronics, for hybrid photovoltaic solar cells, energy harvesting and storage, and also nanodielectric. So we have this theme for, let's say, for energy application, and more generally, we are working on different polymer and nanocomposites. We are working with some industry to try to understand the polymer blends for automotive application. We are working on plasma polymer, bioglue, bacterial films, and recently cosmetics with L'Oreal because we deserve it. So what are the equipment that you are using in the lab? So scanning probe microscopy. Just in a nutshell, what happens for the scanning probe microscopy? All the physics is located at this green pyramid, scanning located at the end of the flexible arm. And by looking, I'll just run it again, by measuring the deflection of the laser shines the back of the cantilever, you can have information about the topography. This is what scanning probe microscopy is doing by using different tips, different coatings, and so on. You can address not only the topography, but also the mechanical properties, electrical properties, magnetic properties, thermal properties, and the coupling of that. Okay? This is one way to get picture, 2D or 3D mapping of the topography and those properties. But you have also another mode, which is spectroscopic. So you see this point located there, and I'm going down, which means that you are sitting on a pixel of the picture and you are making some spectroscopy. In fact, you are recording the force curve. And from this force curve, by using some specific model, you can extract mechanical properties and all those properties. And then you can remap all these parameters at a given pixel, and then you are jumping next to the pixel So we have the imaging and spectroscopy mode. Okay. So the tool that we have is a EFM tip. This is about 2 millimeters. We can see it. The cantilever, before a certain age, you can see this elongated cantilever. The tip, no way to see it because it's few microns. And so you are manipulating this tip and put on the tip holder, and you are measuring, as I mentioned before, for imaging technique. So what are the modes that we have at LPNE? So first, you are using the topography. For the topography, we have the contact AFM, tapping mode, non-contact peak for tapping. All these modes are able to tell you about the topography of your system. Now, if you want to measure the mechanical properties, you have all this zoo of technique. Depending on how you are exciting the tip, you have the contact, which means that stay in contact with the surface. But if, for instance, the surface is soft, we'll drag some material, which means that there is no way to get to accurate topography. That's why in the 90s, people invented the tapping, which means that you are touching lightly and you are measuring the topography just when the tip is hitting the surface. Okay? And then you can do some contact resonance. The tip is in contact with the sample. You are shaking the sample below the tip, and you are able to extract some mechanical properties. So you have this situation. For people who know about dynamic mechanical analysis, it's possible to do it at the local scale. So you have the tip connecting the sample, and you are applying different frequencies. And from these different frequencies, you can have the storage modulus, loss modulus, tangent delta, that people working in polymer science know very well. Now it's possible to do it at the local scale, at the nanoscale. Okay. I will not talk about that today. So you have the mechanical, you have the electrical properties, and once again you have the zoo of technique, probing the dielectric properties like the scanning microwave impedance microscopy. You can have the photodetecting AFM. I will show you some example later today, and the Kelvin probe force microscopy as well to see the open voltage in through the cells, for instance. When you are coupling mechanical and electrical properties, you have the piezoelectrical properties. In this case, we have the piezo response through microscopy, switching spectroscopy, and electrochemical strain microscopy. These modes are new modes that we are developing together with some companies like Bruker, for instance. So on the other side, you have the thermal properties. You have the electrical properties, and when you're coupling electrical and thermal, you have the thermoelectrical properties by using special scanning thermal microscopy with special tips. Then you have electrochemical properties. You have a cell, and you can measure by using the tip being one of the electrodes actively or passively, and you can follow, for instance, some oxidation processes, or you can follow some electrochemical reaction under the tip. Then you have the chemical itself, which means that in that case, you can make some nano-infrared microscopy, which means that you are shining the tip with the infrared laser, and when the polymer or the material is absorbing this, the sample is expanding, and you are following this at different frequency, and you can reconstruct the equivalent of FTIR spectrum. And then you can, of course, clearly identify who is who on your picture. So you have the chemical signature of your system, and then you have the magnetic properties by coating with cobalt first. So we have in LPNE, we discussed yesterday after 20 years, so we finally got all the modes, and we are surfing on the new one, collaborating with the companies. So we have really a kind of Swiss knife of scanning thermal microscopy, which means that you can address a lot of properties with those microscope. And practically what we have some multimode. We have multimode in glove box if you want to work on batteries, for instance. We have this system equipped with different electronics to drive all these funny modes that I just skipped, but to measure the electrical properties. This is one electronic from intermodulation AFM to make some viscoelastic properties. So this is the platform for the mechanical properties. We have the alignment stage. Is it clear for you with the line? Yes, on the back. You can see clearly the slide. It's okay. So we have the alignment station to put the laser on the tip. Then what we have for the contact resonance, as I told you, we are shaking the sample just beneath the tip. So we have two shakers, and we know the answer. It's also called acoustic scanning probe microscopy. We have the dual setup to make nano DMA, so which means that you can eat the sample or change the frequency, and you know there are the time temperature superposition theorem, which means that you can have the master curve of the answer. The answer is solicited at one frequency or one temperature. You can extrapolate and know. You can have information about one polymer, one material at another temperature or another frequency by building this master curve. So we have another, so this is mainly for mechanical properties, so we give name to this microscope Newton for obvious reason about mechanics. And so we can also put some electrical modules and we can measure the piezoelectric properties. This is the electrochemical cell to make some measurement on that. And most interestingly for today, for the photoconducting EFM, what we have here the red line is nothing else but an optical fiber. And the light is just reflecting at this position as the mirror and shine the photovoltaic solar cells, which means that you can measure the photocurrent or the photovoltaic generated in situ in the system. Okay. So this. So this is the platform that we have. This is the Belgian sun, but I saw that we have the same here. But luckily correct. So we have solar simulator with the BM1.5 system, and so we can have the photoconducting data. We can also use this system by putting some UV LED, and we can try to see the photo switching processes on molecule, for instance, as a molecule, for instance, it's more for chemical department, but by using that. Or if you know the stereolithography, you can use SLA, and the idea is to map the mechanical properties once you are using this 3D printing system out of polymer, you have a solution of polymer, and the UV light will photopolymerize, which means that it will become rigid, but you can follow the mechanical properties by using this equipment. Of course, if you are working with perovskite or not stable materials, it's extremely important to work in closed box. So either you have a glove box, or if you want to combine the photoconducting and the glove box, we design this closed chamber with a transparent bottom, which means that you can analyze perovskite by using this piece of equipment. This is what we have here, so on the top of the photoconducting. So we recently got another system more for electrical properties, and the acronym of this of the project that I wrote was Ipanema. You know where Ipanema is. And so this is the acronym for the Intel University platform for emerging materials, something like that. But that's why I said I should go and visit Ipanema. Of course, it will be for this weekend. Don't worry. So we have this Ipanema. This is for the Maxwell icon system. So we have all the modes that we discussed before, and we have some electronics to run these modes. And most recently, we got this scanning microwave impedance microscopy with some special tip. And you can measure directly the permittivity and the conductivity simultaneously. It means that you are sending a signal, get the impedance, you see, remember from electrical lecture, and from this impedance you have in phase, out of phase, and you have the conductivity and the permittivity locally, which is extremely important if you want to measure, for instance, dielectric system. We have on the system this tensile banding and bending stage, which means that you can deform. If you consider flexible electronics, you are measuring the performances, then you deform and you see if the performance is okay or not. You can bend or you can compress or elongate the system. So this is not AFM, but this ESEM. Less impressive than the ESEM that you have here, of course, in all the microscopy that I had a chance to see yesterday, but we on this ESEM, of course, we have EX, we have different cooling stage, heating stage, and so on. But what we will have soon, is the system from Nanovision, which means that you put the SEM stub over there, and you can have here an AFM probe, which means that you can measure SEM with all the beautiful picture that you can get with SEM, including the chemicals you get to with EDS. But you can combine and make a correlation by measuring mechanical properties, electrical properties, piezoelectric properties, magnetic properties, and so on. So this is an equipment that hopefully we'll get by the end of this year. So with that, we can measure all these properties together with ESEM facilities. Coming soon. Another equipment that we will get soon is a lab run from Oriba. It's a Raman spectrometer. But by coupling this Raman with this SPM once again, we will be able to combine scanning probe microscopy with a Raman analysis and pixel-to-pixel analysis. So this is linked to scanning probe microscopy, but with these two equipment, plus all the modes, we can say that we have a lot of, maybe too much, SPM, because we need students, PhD, postdocs to run them. That's the problem, that's the issue for the moment. But we have internship and possibility to welcome PhD students, including, of course, some people from the group of Alex or others. We can try to find them. Okay, this equipment will also come very soon. So, I just take some water and we continue with some examples. So, and I'll choose some examples just to illustrate what we can do with this scanning probe microscopy, and I will focus on different applications. And the first example, of course, will be based on conjugated polymer. This is the Nobel Prize of Igor Yarmit and Hideki Shirakawa. So for the discovery and development of conductive polymers, so what is a conductive polymer? It's a polymer where you can see tunnels of single and double carbon-carbon bonds, which means that you have pi electrons. Those pi electrons can move around the polymer chain and provide some electronic properties. And you have some example, the well-known polythiophene, polyfluorine, and all these. This is the historical polymer, the polyacetylene. And by using this polymer, this is a historical sample because it was the very first sample conjugated polymer that I studied in the 90s. Yes, 91, something like that, last million. This is a polymer coming from the group of Klaus Wieland at the Max Planck Institute in Mons. So it's 8 units of fluorines, this molecule, this polymer, and some ethylene oxide oligomer. So you look here, you can see the topography, and you can see here the phase. And what we see actually is the fact that we have some fibers, and the width of those fibers is corresponding to the length of the molecule, which means that the molecules are packing like card, you play card, and it's just by self-assembly, by interaction, are creating those fibers. And we were able to measure the width of this fiber, and we can also make some modeling with my colleague, and you see here that the width of the fibrils is corresponding to the length of the molecule. And we study a lot of systems, tens of systems, and always we find that it's possible to have self-assembly of those molecules to create some semiconducting nanowire. And we can use that for field effect transistor, we can use for different applications. And I will show you some example photovoltaic. So this is one example of the P3HT. I don't know if you can see here the fibrils, very nice picture with fibrils of 16 nanometer corresponding to the length of the P3HT polymer. This is the formula of P3HT. Exil is the chain of 6 carbon on the side. So just in a nutshell, how an organic solar cell works. So we need an acceptor and a donor. Okay, we have the interface, and typically we need only 100 nanometer to absorb the light. In contradiction on silicon-based solar cell using all lengths, And when you have this, the idea is to create a bulk heterojunction between the two polymer. So when we switch the light on, we shine the light through a transparent electrode, what you have is this. So this is the energy diagram. What happens? The light is coming, generating an electron-hole pair. This electron-hole pair is moving where? To the interface between the donor and the acceptor, then separate. The electron is going to the cathode and the ore to the anode, and you are generating a current. Okay? So which means that if you want to understand, to improve the capabilities of these solar cells, it means that you have should control the morphology of the nanoscale. And this is why the scanning probe microscopy is one of the equipment able to measure or to qualify, to have information about the bulk heterojunction and the level scale. Ideally, and I will come back later on this example, ideally is to have a large interface between the donor and the acceptor. So this is the ideal situation to have the best solar cells, organic solar cells. So if you want to measure the electrical properties, what you are doing, you are using the same tip as before, unless that you are coating with a conductive layer. And you are measuring the current going through the tip. Of course, it's grounded. This is grounded. We have a circuit over there. And you are measuring the electrical properties. And in this case, we use a well-known blend for organic solar cells, which is nothing else than the P3HT and PCBM. This is the C60 soccer ball. I know Brazil is quite strong, unless 2 days ago. You know, for the soccer ball, more than 2 days, C60. So what we did on this picture, we just apply a voltage between the tip and the sample. We see nothing, and you see that gradually we can see some stuff over there. And if we zoom, we can find back those fibrils of P2HT and some black zones, which are nothing else than the PCBM cluster. So it's possible to measure the electrical properties by changing the voltage between tip and sample. So another example, this is carbon nanotube with P3HT. Are you sure you can see the contrast on the back? Yes? Okay. Maybe I'm too old and I don't see the contrast. So what we have here one of the electrode. We have the carbon nanotube with the P3HT. You have here another zone. So this is the topography, this is the current. You can zoom on this region. So we have the carbon nanotube there, okay, with some P3HT growing perpendicularly to this carbon nanotube. And this is the current. So we have the carbon nanotube there, and we have the current over there. Now, we just zoom out. What we have here, we have topographic aggregates of carbon nanotube and P3HT, but no current, because this cluster is not connected to the electrode, which means that we can discriminate and see, for instance, the percolation threshold, the percolation of the charge through the find the pathway to measure electrical properties. So what we have this with conducting AFM. So we change the voltage. So now it's positively, we have the carbon nanotube, which is like this. Green means positive, then no current, and then we have the red. We were extremely happy with that. We measured the IV curve locally on the carbon nanotube. We have anomic behavior, and on the P3HT we have SCLC regime. We were happy, and we got this very nice picture only once. Because when you are measuring that, by using this technique, the coating is removed, which means that you still continue to measure the topography, but no current anymore. What to do? So what we did, and this is David Ginger from Washington, patience and the willingness to sacrifice many AFM cantilevers in the name of science are often necessary. If you are a tip manufacturer, you are extremely happy with this sentence, which means that each time you have to change the tip if you want to get a picture. Come on, we are scientists, we are not buying tips just the beauty of buying tips. So what we did, and we combined with a technique which shows peak force tapping, which means that you are making force curve and you are measuring the current while you are measuring the topography. So you have the force curve, and out of that you can extract some mechanical properties. I will not detail here, but by coupling this peak force tapping and the Q node, the conducting EFM, what you can get is this. And there we have the carbon nanotubes, the P3HE. We can check here that we have indeed fibers of 16 nanometer. And with this tip, you can play one way and start to make science. Change the voltage and see what happens. And you can keep the integrity not only of the sample, but also of the tip. So this is a blend of P2HE and PCBM, and most of the time when people publish that, they say, we can clearly see on this picture the P2HE and the PCBM. The privilege of age, I started with scanning probe microscopy 27 years ago. I'm not able to distinguish P2HE from PCBM. But look at the paper and it's okay, we can clearly see that. Yes, maybe. But in our case, since we are coupling the P3H, the peak force tapping and the conducting EFM for the same price, you can get the mechanical properties. And the P3HC and the PCBM are reacting differently because they have different mechanical properties, adhesion, for instance, young models, deformation, and so on. So what we have here is adhesion. And we can start to see some difference. You see this round-shaped object? Maybe this is the PCBM. So by using one of the channels, here the adhesion, we can make distinction between P3HC and PCBM. So this is the adhesion. We can make the power spectrum density here. What you have two peaks. The first one is at 20 nanometers, corresponding to the length of the P3HC, so the width of the fibrils, and another of about 16 nanometers, corresponding to the size of the PCBM cluster. You see the fibers? You see the cluster there? Even never saw SPM image before. Of course, you saw that you're an expert, but now you can claim that you can distinguish the two. You agree with me? So, our understanding of this morphology of PCBM round-shaped object and those fibers of conjugated polymer, this is the Belgian vision of this morphology. Again. Okay, so coming back to photoconducting AFM, so what we have, you know the Belgian sun now, we have the mirror, this lens to focus on the system, and we have this technique, and no light on the first half, light. We can see a current, and the sample was not biased, which means that the current that you are measuring is actually coming from a photovoltaic processes. So we have here, this is the photocurrent, we have a current, and no current over there, you still have the topography there. So it's possible to use this scanning flow microscope with the photoconducting EFM. So the PCFM is working as an OPV, and we are using the tip as the other top electrode. This is another example here with MD PPV and PCBM. And what we have green region, red region, and black region. And the red region is where we have a higher current. And this red region is just at the interface between the donor and the acceptor. This is where the current is generated, if you remember the introduction about OPV, which means that you can prove visually that the current is generated indeed at the interface between the donor and the acceptor. We have negative photocurrent on the crystalline, there is no light flow electricity produced, and we have just positive, and at the end we have no photocurrent of the matrix because we have this black color of there. told you that it's possible to try to get some ideal photovoltaic system. So what we did, we used TiO2 nano rods to make those rods, and by using P2H2 with the carboxylic molecule here, and we have a strong interaction between this and the TiO2. We make some modeling with that. The whole seminário group did that, and so it means that when you are putting this TiO2 nanostructure in a solution of P2H2, the P2H2 will stick to the TiO2, and then you can use the system as a photovoltaic system. So this is the way of preparing the TiO2. We use the Jensen angle and by shadowing effect. So we are growing and we have the shadowing and we are just changing the angle. So we have slanted column. You put drop cast with P2H2, then you rinse, and you have on top of this nanostructure a thin layer of P2H2. So we have, this is the sample. Sorry for the quality of the picture. So we have the topography on this side. So we just put the sample in the P3 solution. So here, no PHT. Here, PHT. On the top, no light. On the bottom, light. Could you guess what will be the photocurrent in this case? We'll have photocurrent when we have light, of course, and the coexistence of P2H2 and TiO2. This is exactly this is not the picture. And we can start to measure the photocurrent generated with the system with high efficiency for the solar cells. So another technique is KPFM. Just in a nutshell, you know what you are putting two elements. They have, of course, their own Fermi level, vacuum level, and the potential there. When you are putting two elements together, what they are doing, you just align their Fermi level. Remember your class about semiconductor, for instance. And so the idea is to measure this VCPD. It's difficult to measure this VCPD because the force that you are measuring with that. But scanning for microscopy is able to measure force. So the idea is to change the voltage of the tip and try to nullify the force. And when you are measuring the voltage, you are applying the system to nullify the force, you have the VCPD. Okay, this is exactly what KPFM is doing. So we have another. This is MDMO for the chemist. I'm not able to read the name of this polymer. So we have the topography, we have the adhesion because we have the mechanical properties, and you see the potential, no light, and you see a switch of few electrovolts just by switching the light on. You see the photovoltaics are generated out of that. We work also on perovskite, with ammonium perovskite. So we just compared two routes, the one with lead acetate by using this technique, just spinning, drying, and we have then an imaging sample, or the lead iodine route, and we just wanted to compare because of the drawback of this perovskite is humidity, and we are destroying the performances of these perovskite by using by exposing them to water. So what we did, we made AFM in the ALD chamber, atomic layer deposition. And what we did, we put one layer after another layer of water and see the early stage of degradation of perovskite by following the photovoltaic. Okay, good point. So we have a sample, we measure the photovoltaic, and we add water layer by layer and see what we observe. So this is the topography, the work function, and the current. You see, you have some grade of perovskite reacting one way and some region reacting differently. In fact, it depends on how the termination function of the perovskite crystals, depending on all the chemical structure of the perovskite. So this is with lead acetate and lead iodine. So we have this nice current. So we switch the mode, but on the same place. So we have the work function and the current. And this is what Jaume did during his PhD. You see that for the MAPI, at the beginning, when we have few layers, you see that you have this part of the where the MAPI is destroyed and then stabilized. But if you are considering the lead iodine, from the beginning, there is no influence of the water on the on the photovoltaic, which means that by using this route, you can work in open air. There is chemically a reaction that you avoid to destroy your system. So, just remains me 9 minutes before the end. I will just go to flexibility, just to show that flexibility, electronics become flexible, either for electronics, in electronics, tags, or phone, smartwatch, solar cells, and so on. So we need flexibility. And to do that, we need some new electrodes. And one way to do that, in collaboration with people at the Université Catholique de Louvain in Belgium, with Georgiana Sandhu, what she did, she used a silicon wafer, and by electrochemical attack, she was able to create those nanowires, or those nanostructures, which means that now the silicon wafer can bend and keep the electrical properties. This is one way to do that. What you can do also, when you have those nanowires, just peel off the surface and you have semiconducting nanowires, and you can mix them with carbon nanotube. This is extremely complicated image to get because it's a dish of spaghetti. You see it's flexible, but you see it's quite rough. But you can distinguish, I guess, on this. Yes, we have this silicon nanowire wrapped with multi-wire carbon nanotube, and you can use these electrodes for batteries, for instance, or for light-emitting diodes. So this is another example here with this nice silicon nanowire. You see the size is 2 micrometer. We have the carbon nanotube over there. So if you want to study, for instance, the piezo resistance force microscopy, what you are using is electrochemical strain microscopy with a collaboration with people at Oak Ridge National Lab in Tennessee, where the bomb was produced a long time ago. So the idea is, when you are looking at the battery, you have lithiation, delithiation processes, which means that lithium is incorporated into the electrodes of graphite, for instance, and modify it. So by following the, like this, lithiation, delithiation, you can follow the process of charge and discharge within the battery. Okay, this is one way to do that. Another example of the technique, I just showed the technique for the piezo response force microscopy. The idea is to try to get the hysteresis curve, from piezoelectricity. And to do so, what we are using is a spectral switching of PFM, which means that you write something and you measure when you measure at this place the read voltage in the red. You apply voltage and you measure in red, and you are doing that for different voltage, and you can create this PFM response. The problem with AFM, with PFM, because you are measuring charge, and there are plenty of artifacts, because you have charge on the tip, and you are measuring on the conductive or semiconducting, which means that you have a compensator between the cantilever and the sample, which means that you have electrostatic force between the tip and the sample. That you are measuring force, which means that you are measuring larger value than the actual value. And there are plenty of papers coming from big groups mentioning we are able with this material to measure this piezoelectric coefficient, which is 300, and they are killing all the people, they are measuring correctly. We know theoretically, let's say it's 40. They claim they have 300. You are coming with your experiment. We have 30. It's a referee, okay, 30 compared to 300, guys. You got the point. So they are really killing the field and the community because they are measuring wrongly those parameters. So now, together with some colleagues, we are revisiting this technique and see, okay, this is the protocol to correctly measure the coefficient by using, for instance, this electrostatic blind spot, by putting the laser not at the apex of the cantilever, but this magic point. You can measure and compensate actually the electrostatic force acting on the surface. So this is, for instance, an example of PVDF, which is a piezoelectric polymer in which we incorporate bismuth fluoride or PFO oxide, and we have this hybrid system with very nice, flexible piezoelectric properties out of this compound. The scanning microwave impedance microscopy I will show you before, and this is a technique that we can use with the sample people in the group of Alex. We can measure the resistivity and the conductivity of samples by sending at 3 GHz a signal, measuring, because we need a special tip, and we are reflecting, and we are using some working amplifier to get those values. So also, a last example for the last 3 minutes, another way to make some transparent electrode is to use metallic nanowires just to replace the ITO, indium oxide. It's quite expensive, it's difficult to find, and if you want to go and have transparent electrode for organic electronics, there will be a problem with ITO. So the idea is to try to use silver nanowire. This is the protocol. You can find information in this paper. And we measure the figure of merit of this. This is what happens with graphene. So the idea, it must be transparent and highly conductive, which means that if you are on this side, you are on the good side, and with transparency. This is what happens with graphene, black and red, with single wall nanotube, copper nanotube, and silver nanotube. This is the work done by Yu, a Vietnamese PhD. Now he got his PhD last year, and you see that the figure of merit, we are better by using this silver nanowire. And the problem is with this, any nanowires in contact area. So this is the problem. So by annealing or by making some electro deposition, we can try to reinforce the contact between 2 silver nanowire. This is, we use the connecting AFM. So this is a topography, low voltage, and we are increasing the voltage, and we see at 600 millivolt, we can see all the wires. If you are going too high, what you are doing, you are just burning the nanowire, and they are not connecting anymore, even if physically they are there. So we have to find the best way, the best voltage to apply. And then another, by using electro deposition, we have a first nanowire, a second nanowire, and you can see that we can enhance the contact between the two nanowires. And this is what we did also. This is the electrode, 1 nanowire, a second which is crossing it, and depending on how the nanowires are connected, we have high conductivity, like this one, or lower conductivity. And this is what we observe by putting on the 3D, on the topography, the connecting AFM. Here there is no connection because you see there, and at this region, you see that there is no contact anymore. Here we have a huge contact. This sample, this nanowire is just beneath the first one, and in this case, it's just connected in a Y-shaped conductivity. So by using and by measuring this technique, you can see all the population pathway within the electrodes. So we use to make some transparent electrode. You can see here the transparent electrode. Believe me, there is something in the end of here there. This is transparent, but there is something. And what we did, we make some orange light-emitting diode, flexible, and you can play and stay for a long time with high efficiency. So in conclusion, the last 32 seconds before the end of my talk, I try to convince you that by using connecting FM, KTFM, P4 student can have information about electrical properties without imagining the tip and the sample. We saw some example with hybrid system, and this is a very last example by using the scanning microwave impedance microscopy. This is nano-dielectric, the dispersion of silver nanowire in the polystyrene matrix, and we can get the localization of the interface, which is in light blue, surrounding the system. So the take-home message, if you want to elaborate organic and hybrid electronics, you need, of course, a better understanding of the fundamental mechanism, the design of novel or new materials by tailoring energy levels or ability morphology, new process, introduce nanostructure, as we saw for the TiO2. We need to develop application of analytic tool, including scanning microscopy and scanning microwave impedance microscopy, but all the technique. Those device architecture, and this is definitely a interdisciplinary approach is needed to solve this problem. So we need this kind of equipment to be able to try to understand and to solve, not to save the planet, but try to find a way to get some energy for the future generation. Obrigado.
Well, just a comment. You know, I work with material science, but never working specifically with scanning for microscope. And then after starting to work the project and visiting your lab, and now watching your talk, we realize how rich and broad this technique, not just the topology, topography, but a very wide possibilities in the lab. Yeah, it's amazing. Well, questions? Of course.
I worked with SPM, but I have no idea you can do all the stuff. So thank you very much.
You're right.
So I have 2 questions about the photoconductivity. Photoconductivity. The sample needs to have the contacts or not? You just have to put on a transparent substrate?
So you have to contact the electrode. The bottom electrode should be and must be contacted.
I think I lost
For instance, because what you are measuring, so you have a bottom electrode, you have the active layer, and the tip, conductive tip, is your second electrode. Okay?
Oh, okay, okay.
But you have to.
The tip is the other, is the metallic.
Yes,
And
because
you
it's a
have
platinum iridium coated silicon tip on top to measure the current.
Oh, okay, okay.
Let me show you. Sorry, too many slides. You see here, the gold thing is collected via this terminal block to the ideal electrode, or silver nanowire. I mean the bottom electrode. Of course, you need to collect the current between the bottom electrode and top electrode, the current that you are generating with the photon coming from the solar simulator or
About the new equipment.
the future one or the new one?
Yes, the Hammond, with the Hammond.
Yes.
Which laser lines are you going to have?
At the ID, we put some QCL, 4 QCL, and I don't have on top of my head the range, but it will cover, let's say, what people are doing with graphene. Of course, you can change the laser.
Oh,
And for the moment, for the infrared, I know it's from 900 centimeters -1 to 2000, something like that. So it can a wide range for the infrared, and for the Raman, it depends because we will order it, so we can choose and can tune which source of laser, but it's covering definitely what people are using usual Raman, because this is a Raman. It's first a Raman spectrometer, but together we designed with them a way to, the light is going directly as the photoconducting FM on the side of the tip, a little bit terse, tip and has Raman scattering. So the idea is there to make some terse, or just come from the bottom with the light and measure the Raman signal. So we are still working on the design of the equipment. But for the sources, we know, I mean, we will choose which one depending on the model we have to do. It's extremely expensive to source of laser. We cover a larger spectrum.
and about the impedance.
Yes.
The sample needs some treatment, or
No.
you just have to put on the.
That's the beauty of this. There is no need to have bottom electrode. That's the beauty of the
and substrate, and or you have you need a
Yeah, if
capacity?
it's conductive or direct properties. If not, of course, we measure something. But if you take, for instance, silver nanoparticles in a polystyrene, which is not necessarily conductive, you can see this is the very last picture that I showed you. You can have direct contrast this. Because you are sending and measuring on the top of the surface, there is no need to measure, to have the contact, the bottom contact.
Thank you.
Yeah, ask you. Sure. About the peak force microscopy you made, it's possible to you make topography initially the old way. It's a topography with the conducting mass, right?
Yes.
So as you mentioned, just one time, and then you move to peak force. So the tip is the same, just
No,
as
the tip must be conductive.
it's conductive, but the same like
Yeah.
the same. You just changing the way of measuring. Just instead of contact, it's like a
Yes, you are just measuring pixel by pixel, and when you are in contact, which is at the Z region, you are measuring the current. You can measure the current between the tip, when the tip is in contact, let's say from this point to this point, or measure the maximum of the when the force is applied, and you map the current in parallel to the topography and the mechanical properties.
This is a small change. It's possible to enhance saving the lifetime of this.
Exactly. Exactly as the tapping mode did for the first contact.
Any question?
About the perovskite preparation, the thin film. Yes, one question. Is it not important the thickness of the thin film?
No.
No, that doesn't matter.
Of course, it will be, if you want to measure the photocurrent, should be absorbed. It's too large, you will not collect the light on the side of the sample.
Okay.
A few tens of a nanometer.
Because I expect the control should be the thickness, not the.
No, this is really the grain size is important, grain boundary as usually in physics, and how the crystal is terminated. So let me know now.
Any other questions? This?
Hello, Professor. I have about two questions. On the junction between the TiO2 and the powder,
Yes.
it's a chemical bond process or just an absorption process?
No, it's a chemical. This is called cathay color. This is a COOH, and this just linked to the it's more than physics option. It's really a chemical reaction between TiO2 and the P2H2.
And for the luminous spectroscopy,
Yes.
you were using a DC current, yes?
No. Why?
I was wondering if you could have any measurements on a AC current on the sample.
No, because you are sending at a given frequency. So you are not playing. Of course, you can use an AC at this frequency and a DC to make after by using locking amplifier. This is how you can get the amplitude in the phase as usual locking amplifier. Yes, you have DC, but the most important signal is this microwave at 3 GHz.
Another question? No? So let's thank Professor Philippe again.
Thank you.